Okay, this is the lesson on molecular and empirical formula. I talked yesterday about the fact that chemists years ago did not have the theory of atoms in order to determine what a formula was, and so therefore they expressed the identity of a chemical in terms of percent composition. And now I want to go through a procedure that the chemists of a long time ago would have done in order to determine those first chemical formulas from their percent composition. And so this is a method that they would have used, very similar to what they would have used, not exactly the same, but very similar to how they would have determined different chemical formulas. Now, before I go over this procedure, I want to talk about what an empirical formula is. Remember, the word empirical implies, or actually it means that that we're getting it from experiment, and that's the origin of the term empirical formula. It's a very simple formula that we can get from an experiment, and now it's got a slightly different meaning. It turns out that an empirical formula is the simplest whole number ratio of atoms in the compound. And in a moment, I'm going to put up another slide that's going to kind of explain this a little better. Let me just keep reading here. The empirical formula only indicates the types of atoms and the ratio in which they're found in an entity. All right? So it's that simple whole number ratio. What we want to differentiate here is between, say, a molecule and an ionic compound. For an ionic compound, the actual formula that we have is its simplest formula. If I had something like NaCl, and I get that from crossing over the ones, then even though sodium chloride is a salt and is made up of a bunch of repeating sodium chloride units, its formula, even though it's not a molecule, is the same as its empirical formula. It is in the simplest form that it possibly can be. And that's because we divide out the common factor. In this case, there was no common factor. But for actual molecules that are little groups of atoms and not made up of, an ionic structure, they can have numbers in them that are not canceled out. In other words, they can exist in something that isn't the simplest form. Now let's take a look at water here. Water has a formula of H2O. And you'll notice there's no common factor that we can cancel out. It's literally H2O. That's the simplest it can be. It looks something like this. Now, if I'm talking about something then like hydrogen peroxide, which is a molecule that actually looks like this, it's got 2 units of OH stuck together. And so its molecule is actually H2O2. Its empirical formula would be HO. That's the simplest whole number ratio of hydrogen atoms to oxygen atoms. So that is its empirical formula. We divide out that common factor. Now we know that the actual molecule isn't HO. It's actually made up of 2 HOs to make the molecule. But if we were to determine the formula from experiment, empirically, we would get that simplest formula. CO2, I can't divide anything out. CO2, it is the same. C8H18, what can I divide out of there? I can divide a 2, that's going to get me to 4 and 9. So if I divide a 2, I can get C4H9. Again, the way I obtained that in this case was dividing out a 2. Same with the molecule ethine. Again, its empirical formula, CH. Again, what did I do? I divided out a 2. And C6H6. Whoops, wrong color, but that's okay. Again, if I this time divide out a 6, I end up with CH. So you can see here, even though ethine and benzene are completely different molecules, they result in the same empirical formula. And so we have to be careful sometimes when doing these calculations, but I'll talk more about that a little later on. All right. So then I guess what we're saying is, theoretically, ethyne and benzene would have the same percent composition. They have the same empirical formula. The chemical formula and the empirical formula of an ionic compound will always be the same because the formula unit contains the simplest whole number ratio of ions. That's exactly what I stated about sodium chloride. There's some simple problems there that you can do out of the textbook. That simply is about the definitions of empirical formula versus molecular formula. But let's now continue on and do some example problems on how we would calculate this. So, what does an actual formula mean? What does an empirical formula mean? Well, if we have something like CH2, it means we have one atom of carbon and two atoms of hydrogen. But because we don't like dealing with atoms, they're too small, and we like dealing with moles, it also can be interpreted as 1 mole of carbon and 2 moles of carbon if I had 1 mole of the CH2. And so we can think of it in terms of moles. So if I can take some numbers like a percentage and I can figure out how many moles of each of the elements are within that compound, then I'm on my way to getting the empirical formula. If we're going to start from percent composition, here's some rules that you can follow, and I'll follow those in a moment. Because we're dealing with percentages and we want to convert to moles, we need to assume we have a certain mass, and that mass is going to come from the assumption that we have 100 grams of the substance. From the 100 grams and the percentages, we'll figure out the mass of each element in that particular substance. And because we're looking for moles, we're going to convert those masses then into moles using our molar mass. And from this ratio of moles, we can figure out what the whole number ratio is by dividing out the lowest number of moles. And at that point, you've figured out what your subscript numbers are in your empirical formula. You can read through that again, you can pause the movie and you can write that information down. So let's do some examples here. So now I'm going to have to be doing some calculating, so hopefully it doesn't run too slowly for you. But let's go through the motions. I'm dealing with sodium, and that sodium has 21.6% of the mass. So I'm going to convert that into grams. If I assume I have 100 grams, I'm going to have 21.6 grams of sodium. So essentially I'm turning the percentage into grams. The next element is chlorine, and I have 33.3 grams of chlorine. And the last element is oxygen, and I have 45.1 grams of oxygen. So now I have the masses of each of those elements. Eventually I want to get moles, because I need to determine the ratio of the moles. So let's convert them into moles using their molar masses. I'm grabbing a periodic table here. For sodium, we have a molar mass, looking for sodium, 23. So let's convert that to moles, 23.0 grams for every 1 mole. And let's do the same for chlorine, 35.5 grams for 1 mole. And the same for oxygen, we know this one, 16.0 grams for 1 mole. All right, so that's going to take our masses, and it's going to tell us how many moles we have. Well, let me do that calculation here first. 21.6 divided by 23 equals, and I get 0.939 moles of that. I'm not putting the unit moles because I want to just leave the number there so that we can have a look. Let's keep going with the calculation. 33.3 divided by 35.5 equals, and that's 0.939 moles as well. And finally, 45.1 divided by 16 equals, and that is 2.82 moles. Now we could stop there, we could come up with a formula, but it would be incorrect. We could say that it's made up of Na with 0.939 and Cl with 0.939 and O with 2.82. But those are not whole numbers. I need to bring this ratio down to some whole numbers. So I am now going to divide off that smallest value. The smallest number is 0.939. So I'm going to take that smallest number and divide it off of all of the numbers. 0.939 divided by 0.939. That's 1. 0.939 divided by 0.939. That's also 1. 2. That's a 2. I'm just going to X that out. 2.82 divided by that smallest number, 0.939. So let me do that calculation there. Divided by 0.939 equals, and I get 3. What that last step does is turns all of our decimal numbers into whole numbers. Now we have whole numbers for the ratio. That means the empirical formula is Na1Cl1O3. And so those numbers become the subscripts. All right? They go into there. Same with the ones. Ones went in there too. We just don't write them in. So let's take a look at what we did. We first took the percentages and simply changed them into grams. We then took the molar mass of each of the elements and found out how many moles we had. We then took those mole answers and divided off the smallest number to make them whole number ratios. And once we've done that, we have our empirical formula. Now there's a couple of little extra tricks that can exist, so let me do a couple more examples for you. Let's do another one here. And again, I'm going to go a little quicker now through the motions. All right. We have, again, an A, 17.6 grams. Next we've got CR, and that's 39.7 grams. And again, I've got O, and that's 42.7 grams. Na we just did, 1 mole over 23.0 grams. Also oxygen, I know, 1 mole over 16.0 grams. And now I need my periodic table for chromium, and I'm reading that it is 52.0, 1 mole and 52.0 grams. All right. So let's go through the calculations. 17.6 divided by 23, 0.765, 3 significant digits. 39.7 divided by 52 equals 0.765, 3 significant digits. 42.7 divided by 16 equals 2.67. Now for the last step, 0.765 divided by 0.765, 1. 0.765 divided by 0.765, 1. 2.67 divided by 0.765, and I have to calculate that. Oops. Just 1 second. Divided by, there we go, 0.765 equals, and this time I get 3.5. I actually get 3.48, 3.49, but that's close enough to 3.5. Now, what are we going to do with the 3.5? We can't have a half of a mole or a half of an atom of oxygen in there. And so in this final step, if I end up with a 0.5, I can multiply all of these numbers by 2 to bring them up to the true value. 227. All right? Which means our empirical formula this time, empirical formula is Na2 Cr2 and O7. All right, so if I've got an odd number in the empirical formula, then I'm going to end up with a 3.5 or a 2.5. It could be any 0.5. Let's go through some other situations that this can exist with. All right? If I have something like an x 0.5, then in order to take care of that, I'm going to multiply it by 2. Now, I can also have something like an x 0.33 in that last step. If I have an x 0.33, then I can multiply that by 3 to get rid of the 0.33. I can even have an x 0.25. And if I have an x 0.25, I'll multiply that guy by 4. And in extreme cases, not very usual in these particular problems, they're higher level problems, I could even have an x 0.20, and I would multiply that by 5 in order to get rid of it. All right? So be aware, in this position right here, in this position right there, I can end up with a decimal. And it's got to be a nice decimal. Okay, it can't be any decimal. It's got to be a nice one. So you'll round it to the nearest nice one, 0.5 or 0.33, and then you'll double, triple, quadruple, etc. All right? So there's another example, but it's like the others, so I'm going to keep going. What if we were given some experimental information? All right? Instead of given percentage, what if we were given some data that came from a true experiment that carries some masses with it? Well, it turns out that this is easier than you might think. This is actually easier than if you're given percentages. And the reason for that is you don't have to change your percentages to grams. You will already be given information in terms of grams. So we don't need to do the first step. We can just start using the information that we were given. Now you'll notice from this example here, it states that this is number 26 on the worksheet. So you will have been given some extra practice worksheet. And this is number 26. I wasn't going to make up a new one, so I'm using the same one as that. Well, let's go ahead and solve this. A sample of potassium sulfate has the following composition. So in terms of potassium, all right, what have I got? Well, I don't need to think about turning a percentage, and I don't even need to calculate a percentage. I could do it, but it would be a waste of time. I have 17.96 grams of potassium that came out of that particular substance. Sulfur, there is 7.35 grams. And in terms of oxygen, there is 14. Whoops, that's not a 14. 14.70 grams. Doesn't matter whether it adds up to 100 or not. They came from experiment. They're going to contain the ratio. And all we have to do now is continue with the same logic. Let's convert these guys into moles. Potassium, I got to look at my sheet. 39.1. 1 mole over 39.1 grams. Sulfur, better look at that one too. 32.1. 32.1 grams, 1 mole. Oxygen, I hope we're not going to the sheet for that. 16.0 grams. Let's get the mole ratio. 17.96 divided by excuse me, 17.96 divided by 39.1 equals, oops, that's an equals 0.459. 7.35 divided by 32.1 equals 0.229. 14.7 divided by 16 equals 0.919. All right. Let's get that whole number ratio. 0.459 divided by 0.229 0.229 divided by 0.229. I'm still using the smallest one to get that whole number. 0.919 divided by 0.229. All right, let's see what we get. Well, the first one is looking like a 2. 0.459 divided by 0.229, and that indeed is 2. 2.004, that's good enough. That one's obviously 1. 0.919 divided by 0.229 equals, and here I get a 4. 4.01. Again, that's close enough to 4. No need to do a multiplication on the last step on this one, so it's a little nice. So what do I have? I've got a K2. Sorry, that's the empirical formula. I've got a K2, I've got an S1, and I've got an O4. All right? So that's how we determine the empirical formula from experimental data. It's no sweat. It's easy. We just take the numbers we're given, and away we go. We calculate. Be aware, you can still have a 0.5 or a 0.33 in this position here, and we'd have to add the extra step. All right? Now, there are some more examples there. I'm not going to go through all of these examples for the sake of time. There is the homework that you can do concerning empirical formulas, and you can also work on the extra sheet. All right? So you can get all this information. From your textbook, but you can also take a look at this video to supplement the empirical formula.